At the atomic level, chemical bonding is a process of optimization. Atoms seek to reach the state of lowest potential energy in their environment. Consider this energy landscape. When an atom is far from a potential partner, it exists in a state of relatively high potential energy. It is inherently unstable. Just like a ball rolling down a hill to find the lowest point of gravitational potential, atoms gravitate toward configurations that minimize their total potential energy. As atoms approach the optimal distance, the electrostatic attractions between nuclei and electrons balance the kinetic energy. They settle into the bottom of the potential energy well. This lowest energy state defines the stable bond. By forming a bond, atoms achieve a configuration that is more stable and lower in energy than they could ever achieve alone. Chemical bonding is fundamentally an optimization problem. Atoms strive to reach a state of minimum potential energy. As nuclei pull shared electron density between them, they lower potential energy through electrostatic attraction. However, this forces electrons into a confined space. According to the Heisenberg Uncertainty Principle, confining electrons increases their kinetic energy. A stable bond forms exactly where these opposing energy forces reach a balance. Think of chemical bonding through the lens of a blanket analogy. Imagine two people, represented here as atoms, existing in a cold environment. They move closer to share a blanket of electron density. This shared space is warmer, representing a lower potential energy state than being isolated. However, they cannot get too close. If they approach too far, Pauli repulsion forces them apart, as their quantum states cannot overlap. The chemical bond is the precise distance where the warmth of sharing is maximized, while the friction of repulsion is avoided. The octet rule is a useful pedagogical simplification. We often teach that atoms bond specifically to achieve a shell of 8 valence electrons, as seen in noble gases. In reality, chemical stability is not about wanting 8 electrons. Atoms form bonds primarily to minimize electron-electron repulsion. According to the Pauli Exclusion Principle, electrons cannot occupy the same quantum state. Atoms arrange electrons to avoid these forbidden overlaps. Therefore, the octet is merely a statistical outcome of these quantum constraints, not a fundamental goal of the atom itself. In modern quantum chemistry, we move beyond static sticks between atoms. Using the quantum theory of atoms in molecules, or QTAIM, we analyze the actual electron density field. We trace an interatomic path between two nuclei, where the density reaches a saddle point. This specific coordinate is the bond critical point. It is the defining signature of a chemical interaction. We are now able to film chemical bonds as they form. Recent advancements in attosecond electron spectroscopy allow us to capture the subatomic rearrangement of electrons during bond creation. By firing laser pulses lasting only hundreds of attoseconds, we can observe the electron cloud shifting from isolated atomic states to a shared molecular state. These movements happen faster than previously imagined. We are witnessing electron dynamics on the order of mere hundreds of attoseconds, a timescale where the fundamental nature of chemical bonding is finally revealed. Traditionally, noble gases like helium are considered chemically inert due to their complete, stable electron shells. However, in 2025, computational models and experiments demonstrated that under extreme pressure, this rule changes. By applying intense pressure, researchers forced the gold and helium atoms into close proximity, overcoming their natural repulsion. The resulting gold-helium clusters reveal that extreme external forces can drive noble gases into orbital hybridization, creating a bond where one was thought impossible. This discovery fundamentally shifts our definition of inert elements, proving that chemical bonding is a dynamic balance of energy rather than a fixed property. Metal-organic frameworks, or MOFs, are advanced modular architectures constructed by linking metal nodes with organic molecules. These highly tunable coordination bonds produce ultra-porous crystalline materials with immense internal surface area. By alternating metal nodes with rigid organic linkers, we create a stable, repeating lattice. This modularity allows us to engineer the pore size and chemical environment within the framework. These pores physically trap gases like hydrogen. This trapping mechanism is essential for efficient hydrogen storage, a critical technology for the 2026 energy transition. Traditionally, calculating chemical bonds requires intense quantum mechanical modeling, solving the Schrödinger equation from scratch for every electron interaction, which is computationally expensive and slow. Machine learning models now accelerate this process. By training on vast data sets of existing quantum information, these models learn to map the potential energy landscape. These neural networks predict the equilibrium geometry and strength of new chemical bonds in milliseconds, enabling researchers to screen millions of molecular candidates with unprecedented speed. The landscape of drug discovery has fundamentally changed. AI-modeled simulations now drive the identification of new candidates, analyzing protein-ligand interactions at record speeds. By simulating how a drug molecule or ligand bonds with a target protein, AI replaces the slow hit-or-miss trial and error of laboratory synthesis. Since 2024, over 45% of new drug candidates were identified using these computational simulations. This shift is replacing decades of traditional, labor-intensive laboratory work with precise digital models. Superatoms represent a frontier in materials science. They are clusters of atoms engineered to exhibit the electronic and chemical properties of single elemental atoms, effectively acting as building blocks for new types of matter. By controlling the internal bonding and electronic configuration within a cluster, we can create superalkyls or superhalogens. These clusters possess an effective ionization energy or electron affinity that mimics standard elements in the periodic table. These materials are highly sought after for next-generation energy storage. By replacing rare earth metals with superatom-based electrodes, we can create batteries with higher capacity and improved sustainability. In essence, superatoms bridge the gap between individual atoms and bulk materials, granting us atomic-level precision to design the next generation of high-performance chemical compounds. Traditional chemical bonds are built for stability, often making materials difficult to recycle. A major trend in sustainable chemistry is designing reversible bonds that respond to specific stimuli, like pH changes or light frequencies. By incorporating stimuli-responsive linkages, we can create polymers that maintain structural integrity during use, but unzip into their original monomer building blocks when exposed to an external trigger. This advancement is critical for achieving a circular economy, allowing materials to be fully recycled at the molecular level, thereby reducing environmental waste and the reliance on virgin feedstocks. At the heart of chemical bonding lies the Pauli Exclusion Principle. It dictates that two electrons cannot occupy the same quantum state simultaneously. When atoms approach, their electron clouds begin to overlap. As the shells squeeze into the same spatial volume, the Pauli repulsion force rises exponentially. We can map this on a potential energy curve. The dip represents the bond length, the equilibrium distance where attraction balances Pauli repulsion. If atoms get too close, the Pauli repulsion forces them apart, preventing the nucleus from collapsing. This force defines the physical bounds of all matter. Density functional theory, or DFT, is the primary computational framework used to map electron density in molecules. By calculating where electrons are most likely to be found, DFT reveals the spatial distribution of electron probability, effectively defining the chemical bond as a region of space rather than a simple line. DFT transforms our understanding of molecules into an analytical landscape. It identifies regions of high density, such as the bond critical point, where electron interaction energy is minimized, providing the precise geometry of chemical stability. VC-bar theory, or valence shell electron pair repulsion, posits that molecular geometry is dictated by the mutual repulsion of electron pairs in the valence shell. By arranging themselves as far apart as possible, electron pairs minimize potential energy, creating the characteristic 3D shapes observed in nature. We are entering a new era of synthetic design, where computational prediction meets molecular control. AI models now predict material properties with extreme precision, allowing us to build custom molecules from the ground up. By integrating reversible chemical bonds, these materials can respond to external stimuli, essentially unbonding on command to facilitate recycling and structural adaptation. This synergy of AI-driven synthesis and responsive materials marks a fundamental shift toward a fully circular and sustainable engineering economy. Chemical bonding is the fundamental resolution of two conflicting physical realities: the drive toward electrostatic attraction and the necessary avoidance of Pauli repulsion. Atoms exist in a state of continuous tension. Electrons are drawn to nuclei to lower potential energy, while quantum mechanics dictates they must stay apart to satisfy the Pauli principle. This dynamic, quantum dance, is the foundation of every material in our universe, from the rigid structures of metals to the complex, recyclable polymers of the future. Ultimately, chemical bonding is matter's resolution to the complexity of the universe, allowing for the vast diversity of life and materials we see today.